In this session, we're going to take a look at operating system structure. So first off, we're going to look at the concept of a monolithic structure, a layered approach. We're going to look at the concepts of microkernels and modules. We'll look at hybrid systems. Then we'll look in a little bit of more detail at a couple of different operating systems. We'll look at iOS and macOS and the Android operating system, and finish off with how we can build and boot an operating system if that's what we intend to do. First off, though, operating system structure. So modern operating systems, as I'm sure you are aware now, are very large and very complex. Now, a common engineering approach when creating an operating system is to create it using modules. So each module is a well-defined portion of the system with defined interfaces and with defined functions. So this is similar to how you write functions when you're performing good coding practices, as I'm sure you've learned in your C programming course. So you don't just create a main and then slam all your code into one big main. I'm sure you've been discouraged on doing that. You want to think about your design in a modular sense. So let's look at how operating systems, some ways in which they are organized and using this sort of approach. So the first approach we're looking at is the idea of a monolithic structure, so one big structure. So the simplest structure is what we call the monolithic structure. So we place all the functionality of the kernel into a single binary file. Now the original Unix OS kernel, the original Unix OS used this, so it had kernel and system programs all in a single binary file. And the kernel is further separated into a series of interfaces and individual device drivers, right, to give access to, for example, peripheral devices. So everything is in a single address space, which makes it difficult to extend upon. It's what we call tightly coupled. But the simplicity of it makes it very fast. So as long as it does what you want it to do and you don't need to make any changes to it, then this structure might work okay. The second approach then is the layered approach. So with the layered approach, the system is broken into a number of layers, and you can see it here. I guess you could think of it as like an onion, right? So an onion has a bunch of layers. And in the middle, in the core layer, is layer 0, hardware. So we go from layer 0, hardware, to layer N, which is the user interface. So separation of the hardware from the user interface. And so changes in one component do not affect any of the other layers. So computer networks like TCP/IP, they use the layered approach, right? So if you remember to your networking course, you probably talked about, for example, the OSI model and how approaches to networking involve breaking things down into layers in order to define certain pieces of functionality that one layer can perform. Now, this particular approach, this layered approach, which is popular in networking, is not used as much in operating systems. The microkernel approach structures the operating system by removing all non-essential components. So the non-essential components are implemented as user-level programs, and so they have their own address space. So we keep the kernel very small. And its main function then becomes communicating between the client programs and the various services that are running. So it acts kind of like an intermediary. And this approach then makes it very easy to extend the operating system because we can just add on user-level programs and various services. And it also provides security. So most programs are then run at user level. And if they're run at user level, there's not too much damage that they can do. But there's increased overhead because there's more communication between these client programs and the services. So increased overhead between them. So the best current methodology is one called modules, or loadable kernel modules. And this is common in modern implementations. So for example, in Linux, Mac, and Windows. So the kernel then provides the core services, right? And we've seen that. So separation of the kernel from the user. So other services are implemented dynamically as the kernel runs. So the overall result is a layered system then, right, with user and with kernel, where each kernel section has a defined and protected interface. We can only access the kernel through those interfaces. But it's more flexible because any module can call any other module, as we'll see. And then lastly, the hybrid system. So very few operating systems implement any of the preceding strictly defined structures. So those are more abstract structures. Most combine them in a kind of hybrid form. So for example, Linux is monolithic, so a single address space, but it also is modular. So new functionality can be dynamically added, and of course that makes sense. It's why one of the reasons why Unix is so popular. You can kind of configure it the way you see fit. And so three hybrid systems that are worth looking at then are the Mac operating system, the iOS, which is of course what runs on iPhone devices, and tablet devices, iPad devices, which my daughter is a big fan of, and then Android, which runs on smartphone devices that are enabled for Android, which is of course managed by Google. So first off, with Mac OS and iOS, Mac OS runs primarily on desktop and laptop computers, so it's what I'm using right now to present this to you. Is I'm running a Mac OS that allows me to use the tools that are available for creating presentations in this program. So iOS runs on iPhone and iPad devices, so there are some similarities. So the general architecture of both is quite similar. So apps can bypass or take advantage of certain layers. So you can see here that an application can use the user experience layer, application frameworks layer, and core frameworks, or it can access directly to the kernel. So that has a lot of flexibility built in there depending on what your preferences are during the design of your application. So what are some of the differences? Well, Mac OS is compiled to run on Intel architectures. Also, these days, ARM architectures. So this system that I'm running on right now, this laptop is using ARM architecture. The M2, I believe it's called. iOS is compiled to run on only ARM architecture. ARM architectures are predominant on mobile devices, right? Modified to address things such as memory and power management, which are much more important on smartphone devices than laptop devices. The iOS is also more restricted to developers, and that makes sense because resources are much more limited and require much more careful consideration. So if you give app developers more freedom, it's possible that they can create applications that, for example, drain your battery in a very short period of time, and that can be quite frustrating to users who may blame the iOS then when in fact it is perhaps the application developer. Next, Android. So Android is run on smartphone devices as well, but different smartphone devices. For example, non-Apple devices like Samsung, Huawei. There's so many different Android enabled devices out there. So it's developed primarily by Google for Android smartphones and tablets. It's open source and it runs on a variety of platforms. And it's similar to iOS in its layered stack of software. So we can see over here on the right-hand side that up at the top we have our applications. And interestingly enough, you can see that the Android device, the Android stack includes a Linux kernel, or it's a modified Linux kernel before accessing the hardware. And it's primarily developed using Java. So if you're an application developer developing Android applications to run on Android, then you need to have a good understanding of the Java programming language. And again, notice that it runs on a Linux kernel, although it's slightly modified. So it's optimized for efficiency, memory usage, and power management, of course. And another thing on that previous diagram is you might have noticed a layer there called the HAL, or the hardware abstraction layer. And this layer is there to give it a consistent view of all hardware. And this is what allows Android to run on so many different device manufacturers. So you can write programs in that are portable across different hardware platforms. So it doesn't matter if it's a Samsung phone or a Huawei phone or any other kind of phone. So it ensures there's no limitations to application development, which is, the point I'm making. You can just design an application and make it available, and any device that's Android enabled should be able to download that application, and it should run seamlessly. And again, the Linux kernel has been modified to support mobile usage, and that makes sense. Mobile devices have much less resources in regards to memory and power than, for example, laptop or desktop devices would. Yeah, so for example, power management optimization, that's a big deal. Lastly, I just wanted to take a quick look at building and booting an operating system. So when you buy a system, it usually has an operating system installed these days. But you may want to install your own creation. So you may, for example, what I've done in the past is purchase cloud space and then install the operating system on top of a empty virtual machine and configured it accordingly just to do some development work. So if you want to create your own, you can write the operating system source code, right? Which is you can take Linux, for example, and start adding on your own modules or modifying modules that are there. So basically, you're just modifying C code. Or you can find previously written code that's already there. So that's the first step. The second is configure the operating system for the system that it will run on. And then compile the operating system. So configuring the operating system for the system it will run on is the first step, that compiling the operating system. And this is known as a system build. Okay. Then once you've got a system built, then you need to install that operating system. Or the next step is to install that operating system. Once it's installed, then you want to, of course, restart. So you boot the computer, it's called, which is essentially a restart. And that should load the new operating system. So after the operating system is generated, it must be made available for use by the hardware, right? And again, this is called booting the system. And when we start up a system, there's a program called the bootstrap program, also called the bootloader. And it's usually in what's called the BIOS, the basic input-output system. And it locates the kernel. And the kernel is then loaded into memory and it's started. So we have a base operating system. And the kernel initializes the hardware. So it does what's called a post to make sure that all of those devices that are connected are working. So it basically checks in with them all. And then the root file system is mounted. So there's a space on the storage device, whether it be a magnetic disk spinning or a solid state device, which is the case on this particular laptop that I'm using. So the root file system is mounted, and then we're ready to go. And then we can start loading our applications on top of the operating system, and the operating system handles the interaction between the application and the hardware. Okay, so that's all I wanted to talk about in this session. So just to summarize, we looked at the concept of a monolithic structure, a layered approach, right? Microkernels and modules. Then the hybrid systems, which a lot of modern day operating systems are kind of a hybrid of these first three approaches. We looked at iOS and macOS and also Android, right, which are considered to be hybrid systems. And then we looked at the basic outline of how to build, the steps to build an operating system, and then also how an operating system boots up. All right, thanks for tuning in.